things back. And so that would be osmotic pressure. Well, now in animal cells and in human cells, the results are what I mentioned. If too much water flows in, the cell just swells up and bursts. If too little water is available, the water gets sucked out of the cell and it just shrivels up, and dies. But plants can go a step further. And so plant cells live inside little wooden boxes. Okay, so they have a cellulose cell wall, and cellulose is the fundamental fiber that makes up wood. And incidentally, cellulose wood fibers are just strings of sugar molecules. And so actually, if you could hold a wood chip in your mouth long enough, it would eventually taste sweet. Now, there are very few things that can really digest wood fast enough for you to notice that. Whereas starch is a string of sugar molecules, but they're put together in a different way. They're easy to digest by comparison. But wood's still made out of sugar, but they're lined up in a way that very few things can digest. But plant cells then have this wooden box around it. And so now, osmotic pressure draws water into the cell. In fact, plants are kind of designed with above average osmotic pressure, so they tend to suck water out of the soil. And so the soil, wet soil, is going to have less osmotic pressure than a plant cell will, and so the water is going to flow from its own high concentration in moist soil through the cell wall and membrane into the living cell. And so osmotic pressure, osmosis itself, as you can think of it as a suction pressure. A cell with a high osmotic pressure means it has a high tendency to absorb water. And so plant cells are designed with that. Now, if the soil gets too dry, and so you've got a little bit of water and a lot of soil mineral, then the soil sucks the water out of the plant cell, and what does the plant do? Wilt. Okay, so that's all that happens when it wilts. But in normal soil, the cell will suck the water out of the soil, but as it does so, it swells up. Well, why doesn't it just burst, like our cells would or an animal cell would? And the answer is the wooden box. And so they have this wooden box, this cellulose wall around them, that stretches. And so the fibers are kind of like this, and there's a little space, and they can stretch and line out better. And so as they stretch, what? They generate a back pressure. And so turgor pressure, I think it'll be down here. And so turgor pressure is the back pressure exerted on a cell by a stretched cell wall. Now, we can't do that because our cell membranes are too weak to really exert any pressure. They just break. But plants have this wooden outer box, and so they can fight back. And as osmosis brings in a lot of water, causes them to swell up, the stretch of the cell water pushes the water physically back out. And so you can reach a balance where water coming in by osmosis equals the water pushed out by turgor pressure. And usually the cell is in a turgid condition. And that means it's kind of firm, full of water. And most normal, healthy plants are like that. You bend them over, and they snap back. When they're wilted, it's a whole different story. And so plants actually use turgor pressure, as their skeleton. And of course, it works very well. Holds redwoods, 300 feet in the air and so on. And so this works quite well. Osmosis drawing the water in, turgor pressure tending to push the water back out again. And so then you introduce this term here, DPD, diffusion pressure deficit. And so that's again kind of a quote suction pressure, the tendency of water to move into a cell. The higher the diffusion pressure deficit, the greater the tendency of a cell to absorb water. And so it's the osmotic pressure drawing the water in minus the turgor pressure pushing the water out. And so those are two competing forces, in a plant cell. Now notice, by the way, that we've already left the animal world and the human world. This doesn't apply to us because we can't generate the turgor pressure. So now we're getting into plants only. And this is where they generate a lot of power. Well, how much power? Okay, and so here you take a look at a little plant, and I'll enlarge the bottom diagram down here. So here you have a plant, and we can think of this as a little seedling just sprouting out of the ground, or a redwood tree 330 feet in the air. And so down here at the bottom, you have moist soil, and the diffusion pressure deficit in moist soil may be virtually, hardly any at all. It doesn't have any tendency to absorb water. The extra runoff just flows over the top. So that would be moist soil down here. I'm not really sure why we put 1 minus 1 there. Just 0 would be a right number, or a tenth. The diffusion pressure deficit of moist soil is usually about a tenth of an atmosphere, not much more. I sketched a little thing here to show you close up what's going on. So this would be a root hair cell. So this would be on the outside of the root. And a lot of the cells on the outside of the root have little hair-like projections. Not really hairs. They're still covered with the woody fibers and so on. But they stick out to increase the area for absorbing water. And so the 6 here tends to be pretty much the osmotic pressure in a typical living cell. And that's based on the amount of proteins dissolved in the cell. And so 6 atmospheres are roughly 90 pounds a square inch. Well, what's this minus 5? Well, a root hair cell that's out there in moist soil is absorbing water, swelling up, generating a back pressure from the cell wall. And so the second figure, in fact, I can go ahead and put those in. The top figure would be the osmotic pressure. That would be the pressure pulling water in. The second figure would be the turgor pressure pushing water out. And so you're going to get to a point, you can subtract these two, and the net tendency of water to move into the cell then is this bottom number. And so at the root hair cell, the root hair tends to absorb water from moist soil. Now dry soil, it's not going to work. But from moist soil, it'll absorb water. The cell wall will begin to stretch, push water back out, but what? It doesn't just push it back out into the ground. It pushes the water into the cells above and below, left and right, and toward the middle. And so some of the water pushed out by turgor pressure goes into the next cell toward the middle of the plant root. And so the plant root, the middle of the plant root may still have an osmotic pressure of 6 based on the amount of dissolved material in it, but it will begin to absorb water pushed into it by the root hair cell next to it. And so its turgor pressure will begin to build up.